Well, hey again, this is Mr. Doro, and this is part 2 of our energy calculations video. So if you haven't seen part 1 yet, you're missing out on some of the basics, and I'm going to be jumping right in past those, so you may want to go back and watch it again. But here we go with part 2 of energy calculations. Just a brief reminder of the heating curve for water, and remember also this could be the cooling curve if you were going back this way. So if you're going down in this direction, energy is being released, and that could be a cooling curve also, and tell how much energy is being released in each section. In this part today, what we're going to do is we're not only going to be dealing with one section, but we may be dealing with multiple sections. Maybe we have to come across one and go to another one and maybe even enter into another one. So it gets a little bit more difficult. So hold on. So for our first problem that we're going to do, we have a water bottle that was put in a freezer. The temperature was negative 15 degrees Celsius. You forgot it was in there. It completely froze, and we're going to assume that it got down all the way to this temperature, negative 15 Celsius. Then you put it on the counter until it all melts, and how much energy was absorbed after taking it out of the freezer. So we're starting at this negative 15. We're melting it all. And so if we really think about this on our cooling or heating chart, we were at negative 15, so we had to come up, and we had to use this part down here to get to the zero. So the temperature had to come up, that's thermal energy at first, and then we also had to go all the way across and use or store some phase energy in that. So we really have two sections that we're dealing with here, temperature versus time. We had it going like this, and then we had it flattening out. So we have to do two different types of problems on this. So going back to our other page, we have our constants for this section right here. It is 2.1 joules for every 1 gram, 1 degree Celsius. And for this section right here, it is 334 joules for every 1 gram. And one other thing that might be helpful before we get started, we need to think about this bottom temperature as being negative 15 degrees and this one at 0.0. So our change in temperature that we had in that bottom section was 15 degrees Celsius. So taking one step at a time, I'm going to start with this bottom section right down here. And in that bottom section, we need to end up finding how much energy. That's what it's asking us to find, how much energy. So I need to start with energy on top. I had 2.1 grams, or sorry, joules for every 1 gram, 1 degree Celsius. But I didn't have 1 gram. Instead of 1 gram, I had 340 grams. So I'm going to multiply that by 340 grams. That's going to take care of my grams because this is 2.1 joules for every 1 gram, but this was 340. And then it also didn't go up 1 degree Celsius. Instead, it went up 15 degrees Celsius. So 15 degrees Celsius, and really that takes care of my units right there. So I plugged in my calculator 2.1 divided by 1 divided by 1 times 340 times 15. And when I do that, I get 10,710. And just 2 sig figs, that's 11,000 joules. Now 11,000 joules was just for this section right here. That was just to heat it up to the point where it could start melting. Now I need to deal with the part where it did start melting, and all of it melted because it says it all melts. So I'm going all the way across this area right here, and when I do that, I need to do another calculation. And so that calculation is going to look like this. I start out with, I again want joules. It is 334 joules for every 1 gram. But I didn't have 1 gram, I had 340 grams. And so that's why I'm multiplying it by that. When I do that, I get 113,560 joules. And so in 2 sig figs, that would be 110,000 joules. So it only makes sense then if this section right here took 110,000 joules and this section took 11,000 joules, it only makes sense for me to add those two together to see what I get for the total amount of energy that was needed, and I get 121,000 joules, and or 121 kilojoules of energy. Now sig figs when we add is different than when we multiply or divide. That's why I ended up with 3 sig figs on there. So that is how we would do a multi-step process. Let's try one more. Alright, so this problem is how much energy needed to be released to make a mixture that is 3/4 ice and the rest liquid of a 665 gram sample of water that is at 50 degrees Celsius. So when we look back at our little chart right here, we're going to see which section we're in. 50 degrees Celsius is in this area right here because it's liquid water, but then it freezes and we're going to go part of the way across here. So we're going to go all the way down to the freezing point, and then we're going to go across a little bit. The temperature in this case is going to go down, 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 and then it is going to even out as it's starting to freeze. So I put the numbers for the constants for the experimental value of the heat capacity and the heat of fusion, and that happens at those stages. And let's just think about what's really happening here. We had liquid water that was pretty warm, 50 degrees Celsius. We cool it down. Once it gets down to 0, then I want to know how much energy when 3/4 of it melts. The rest is water, but the temperature is still going to be 0 degrees Celsius. So we got to take this one step at a time. Let's start out with finding out how many joules it is to cool it down to the freezing point right here. And so this is our constant. We need to find joules, so I'm going to put joules on top. So this is 4.18 joules for every 1 gram 1 degree Celsius, but we don't have 1 gram, we have 665 grams, so that's why I'm multiplying by that. And it did not change by 1 degree Celsius. Instead, it went down from 50 to 0, which means that it changed by 50 degrees Celsius. And so then we plug this in, 4.18 divided by 1 times 665 times 50, and we get 138,985, and I sure wish I would have put a decimal point right there after the 50, so we're going to call that 2 sig figs. Let's pretend I did that. And so that would be 140,000 joules, which I'm going to make 140 kilojoules just because it's nicer to write. And then we are going to take care of the next part, which is the freezing of that, but 3/4 of it freezes. So I'm going to see how much energy that takes. That was 334 joules for every 1 gram, but I didn't have 1 gram. I had 665 grams, and so when I do that, I get, okay, now I get 222,110 joules. But remember, this said only 3/4 of it turned to ice, so I'm only going 3/4 of the way. So I'm going to multiply this by 3/4, and then I'm going to put it in the correct number of sig figs. So really, to multiply by 3/4, I'm just going to do times 3 divided by 4, and I get 166,582.5. I want that in 3 sig figs. That is 167 kilojoules, because remember, I'm changing it over to from joules to kilojoules. So that's what I got for that section, to melt or to freeze 3/4 of it. This one up here was to get it down to freezing, and so I have to add those two together to find out my total amount, which it looks like it's going to be 307 kilojoules total that I had. And that may be 310 because of sig figs, but remember, for adding and subtracting, we never really went over the rules on that. But we need to make sure we know that this is my E total. That's my total energy for that to happen. It looks like E thermal kind of, but I just wanted to say that that was my total, so I'll write total right there. Okay, so here are a couple practice problems that, again, if you're doing a retake, then you really have to do these practice problems. If this is one of your methods that you're doing for the retake, or there's just things that you could practice and try to get more help on those as needed. Okay, I hope this really helps. These energy problems can be really challenging. You have to find out where you're at and what you're looking for, and it really helps. And remember, there are formulas to use these, but we don't do the formulas because we know how to figure it out on our own. And sometimes when we do the formulas, that doesn't mean we really know what we're doing. We just know where to put things in a formula. Okay, thanks. Have a great day. Bye-bye.